All right, one last thing before we leave this section behind. We've talked a lot about truth tables at this point. There was one last notion that ends up coming up that I want to address, and that's what we talk about when we say two statements are equivalent to each other. So equivalence in this sense is kind of like a logical equality. You can think of it as almost two different ways of saying the same thing. As it turns out, truth tables are a useful tool for analyzing when two statements are in fact logically equivalent, when they are just two ways of saying the same thing. So the idea is, if you set up a truth table for each of the individual statements, it turns out if that final column is in complete agreement, so it has the exact same true-false configuration, then the two statements are in fact logically equivalent. Otherwise, they're not. So as it turns out, without even really meaning to do it, I promise that wasn't set up, I actually generated a couple of statements that are in fact logically equivalent to each other. You'll remember a couple of videos back, I did some two simple statement truth tables, and we saw the final column of each of those worked out as false, true, true, true. So those two guys, as it turns out, are in fact logically equivalent. So writing those guys down, so we had P and not Q, or not P. So on the other hand, we had P implies not Q, and it turned out those truth tables matched up when it was all said and done. So we would show these things are equivalent by doing, it's not quite an equals. We do 3 horizontal bars instead of just 2. If you wanted more parentheses, you could put them in here, but this already looks pretty busy, so I don't think it's strictly necessary. I mean, if you wanted to, you could close those up. But so we've already seen one example of equivalent statements. I want to investigate another couple real quick. So let's take a look at this guy. So not too involved in this instance. So we've got two operations. We have a disjunction inside some parentheses, and then after we've done the disjunction, we apply a negation. We want to compare that to what's going on over here. And if you think back to what we've done previously, this may look a little familiar. If not, it's okay. So now we have two separate negations with a conjunction linking them up. So let's take a look and investigate to see if these things are in fact equivalent or not. For the record, if you were having to write this out symbolically and two things weren't equivalent, you just kind of put a slash through there. But all right, let's take a look. All right, so P, Q. All right, I'm trying real hard to avoid more jump cuts. But anyway, so we got this guy so far. Awesome. So we had P or Q. So we need to deal with that guy first, and then we can apply negation to it. Again, a disjunction, the or, is true as long as we have at least one true. That happens everywhere but in this final column. So that guy would be a false. And for what it's worth, if you had just copied that arrangement off the base truth table for a disjunction, that's fine. So now we negate this guy. So that should not be P or P. Oops. It's P or Q. So now we just take this guy right here, and we flip all the true-false values. So we flip the switch, and we've got that guy right there. False, 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 true. Okay. So now, shoot. And it's gone. So now let's see what happens if we go the other direction. On the other side of that thing, where we apply the two negations separately, but then hook them up with a conjunction. Here, we negate the truth and false values of this guy. So we have false, false, false. True, that guy right there should be a true. Note, I made a boo-boo. So yeah, false, false, true, true. This guy, I need to negate what's right here. False, true, false, true. Okay. Now we hook these guys up with a conjunction. Do you guys get the Schoolhouse Rock thing stuck in your head every time I say conjunction? It's weird. I do probably about 1 in every 3 times. So, false and false. That is false. False and true. They both have to be true. They're not. True and false. Same thing. Still not a pair of trues. Not until we get to the bottom do we have a pair of true statements. False, 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 true. You can jump back and take a look if you want, if you haven't been writing this down along the way as you go. This is the same thing that we saw before, from the other arrangement. So it turns out, because these guys line up, the statements are in fact equivalent to each other. So, as it turns out, again, this may have looked a little familiar. We did something kind of similar with set operations. If you think back to that, negations are like complements and unions are like, disjunctions and stuff. There's some overlap. So yeah, it turns out our buddy De Morgan, where we had those set theory De Morgan's laws, back when we were talking about sets and Venn diagrams and stuff in chapter 2, lo and behold, those laws have a logical processing as well. So we've just seen one of them. So essentially, you can sort of distribute the negation, but in so doing, you have to flip the connective that's in between the two. So this disjunction became a conjunction when we spread out the negation. Hopefully it's not too surprising if I flip the script. I'm not going to walk through a verification of this. I leave that to you as an exercise if you want to check to make sure this happens. But it does, in fact, work out that the negation of a conjunction is the disjunction of the negations. That's way more awkward than I was expecting it to sound. So that's a couple of examples of what we talk about when we say statements are equivalent to each other. We're going to see some more of this notion of logical equivalence in the next section. Before we get to that, though, I want to lay some ground rules, some terminology about what we mean when we start playing around with conditional statements. So keep an eye out for that.